right, hello everyone. Good afternoon. Welcome to Applied Data Analysis. For those who don't know me, I'm Alan Jen. I am a researcher at the Institute of Transportation Studies. And this is a course that I've been teaching for a couple of years now that's going to delve into essentially application of regressions and some machine learning, hopefully to help you guys with your research that does any sort of data analysis. Okay. Yeah, and so I think so for a lot of folks who are taking TTP or EG or even in civil, there are a lot of sort of statistics requirements where you learn about things like regressions, and a lot of that is going to be more on the theoretical side, how and why they work. And this course is going to overlap with a lot of those statistics courses, but it's going to be with a much greater emphasis on how you use it in practice, implementation, application, interpretation. And so this is the type of thing that you might see in your typical regression class, thinking about linear regressions, and then looking at these tables and sort of doing the interpretation for results. But a lot of what we will be doing is thinking about raw data, exploring the data, building the regression models, looking at outputs, and then interpreting findings. Yeah, and so again, some of the material, especially for those who are familiar with those statistics courses, is going to overlap. But hopefully you'll still be able to learn quite a bit in this class. Okay, so a quick intro and review of programming. We'll then look at regression analysis, unsupervised learning. I've actually this quarter started adding in a little bit more stuff on machine learning, and then we'll look at case studies and project presentations. I'm not going to talk about the projects today, so if you sort of glance over the syllabus, you'll see that we do sort of course projects instead of finals and midterms, and I'll go into a lot more detail about that in coming lectures. I won't talk too much about it today unless anyone has specific questions. Okay, so the breakdown of the grades are here. Most of it is going to be in homework. Late penalties for homework, 10% per day. And then for the final project, this is essentially going to be analyzing the data set of your choice, employing the techniques that you learned throughout the class. Okay. Any questions, concerns so far?
Yeah, hi, I was just wondering, what's the 30% class participation for?
It's kind of like, to be honest, it's kind of like freebie points. If you're coming to lecture, then that's fine. I mean, I like it when folks participate, but it's more of the typical kind of thing that can help sort of bump your grade up or bring your grade down, depending on how much you attend. And also, given that it's remote, I am sort of also giving the option to watch the lectures, which will be recorded. And I think obviously I think it's better if you're doing it live, because then you can participate and ask questions sort of on the spot. But I understand, teaching remotely, if there are specific situations that make it difficult, that's fine with me. yeah, and so participation is show up and you'll probably get full marks.
Cool, thank you.
Yep. Any other questions or concerns? Okay, so moving on. So we're going to get started with basics of programming. And so this is, I've sort of put together a tutorial in R over the last couple of years and have been building on it. And so this is a way of introducing. So in the prerequisites for this class, there actually isn't any requirement for you to have a background knowledge in programming, but some background is going to make your life a little bit easier in terms of doing the homeworks and seeing how we're doing the application in class. But again, many people have taken this class without any experience in R, and that should be totally fine. It just means you're going to have to put in a little bit more work to sort of keep up. And then the other sort of common question is, there are some folks with who come in with programming background that is not in R. So most commonly it's in Python, and that is fine with me. So if you want to do the course in a different language, that's fine. The only thing to keep in mind is that there will be some things that are a little bit more specific to R that will require you to, it probably just means that there's going to be a little bit more effort to do it in other sort of languages. You're going to have to find like packages or libraries that have the functions that we might be employing. Yeah, and so for today and for the second lecture, we're going to focus on learning the basics of this programming language. It's going to be, I think, for those of you who are already familiar, a lot of it will be review, but there might be a couple things here and there that you might learn in terms of different functions. And so, yeah, I think for folks who have some background, they've usually expressed that there are still some things that they learned in these tutorials. So up to you if you want to stick around for those. Yeah, and so we'll go through a bunch of functions today, some practical things to learn or understand about programming in general, and then I think importantly for data analysis, we'll talk a little bit about dealing with data if you're doing it programmatically, cleaning data as well. Okay, so one sort of quick thing that I like to give as an overview is sort of the world and domain of software that is used in sort of the world of data analysis or sort of connected with the world of data analysis. And this list kind of grows every year. But to give a sense of kind of what's out there, there may be other languages that may sort of closer fit your need. So statistical analysis, everything kind of within this blue circle. So R, I think, is kind of the best suited for this. It is open source software that is designed specifically by statisticians and data analysts. This class of software that you may have heard of in one way or another, SAS, SPSS, JMP, Stata is really common for economists, for example. These are all software packages that also do statistical analysis, but they're actually, all of these are, none of these are free. You have to pay for the software. And at this point, R actually probably has a much larger user base than any one of these. So, keep that in mind. Matlab, for any engineers out there in civil or even mechie, Matlab is a common sort of tool used in engineering. This software is also proprietary, and so it costs money, but if you're associated with academic institutions, you can usually get it for free. The open source version of Matlab is called Octave, and it functions very similarly, and this is actually a common software used for folks who do machine learning. Oh yeah, and so Python is the other sort of open source, free available one that has a lot of overlap with R. That's traditionally been a lot more fundamentally used in computer science applications. It is able to do some kind of programming aspects, especially with the fact that it has like class functions that aren't available in R that lets you do certain types of programming a lot easier. But when it comes to statistical analysis, yeah, there's definitely a split between folks who do R and Python. MySQL or other sort of SQL-based systems and things like MongoDB, these are database software, and so these are really useful once you're starting to talk about data sets that get sort of beyond what you can hold within like the memory and RAM of your computer. And then Ample and GAMS are both optimization software. And so these generically have these optimization algorithms and engines that can solve specific types of problems, or generic types of problems that are meant to be optimized. So actually when we talk about regression and machine learning and data fitting, all of that is actually relies on forms of optimization, but because they are specific types of optimization that follow specific conditions, they already have sort of built-in algorithms that are meant to solve the types of optimizations that we do specifically. And so the more general types of optimization procedures are left to this kind of software. Latex, for those who are interested, is a word processor alternative to Microsoft Word. And so if it's something that you're interested in, yeah, just let me know. It's a good way to apply is actually to learn it through just like doing, homework sets in a class, for example. And actually RStudio, which is what most of you guys will be using, can actually do processing into LaTeX or other forms like R Markdown as a way of sort of generating a document. And then the one that I'm kind of leaving off this list that is by far away the most common data analysis software, Excel, which I'm sure most of you or all of you have some familiarity with. And one thing that I want to make sure not to sort of conflate with is the fact that like if you're doing R or Python or programming, it doesn't mean that you're doing any more like sophisticated data analysis than you could be doing in like software like Excel in a spreadsheet based model. But I think that hopefully we'll be able to demonstrate there are many instances of types of problems and sorts of studies that are going to be just infinitely easier to do programmatically than to do in Excel. There are a dozen examples that I could immediately think of which would take you hours to do in Excel and seconds to do in a programming language. And so that's why we're kind of leaning to this alternative software. And it doesn't mean that you should never use like Excel ever again. Okay. So users, so statisticians are the ones who typically use R, like I said, with Python. It's computer scientists, but also some statisticians, data economists, and then SAS and SPSS. These are oftentimes like social sciences and actually some government agencies. I always mix up which ones use which, use SPSS and SAS. And then in terms of software costs, all the ones that are circled in green are free and openly available, and all the ones in red you have to pay for in some way or another. Oftentimes it's like scaled, right? And so you could get freeware version of some of these, but like you won't be able to add in more than like X amount of data or something like that. Okay, and so that is kind of a quick overview of the world of software, at least that at least mainstream software that I'm aware of that gets into some of these topics. Yeah, and so we'll end here and get into the R tutorial, unless there are any questions, which you can ask while I set up. Yeah, go ahead.
Sorry, I was just going to ask, do you prefer that we submit homeworks in R Markdown, or does it matter to you if we use an R script and then put it in Word?
Yeah, I will, yeah, maybe I'll add, I'll make some slides about that for next lecture, but generally, yeah, I think I've been fairly open about it in the past, but I definitely do find that like R Markdown is probably one of the easiest things, or just like a PDF kind of equivalence for me to do that grading. So yeah, I'll make a little guide about my preferred modes of homework submissions.
Okay, sounds good. Thank you.
Yeah.
Can you elaborate on the homework? Are they gonna be structured, or they are kind of like final project that we have to choose our data set ourselves?
No, for the homeworks themselves are gonna be like specific, like there will be an assignment that I'll post, and then you just work off the problem set.
Okay, got it.
Yeah.
Thank you.
Okay. So the tutorial, I guess it's a little bit challenging, especially for those who don't have two screens. I've been trying to, because I taught this last year during the pandemic, and the way that I basically go about this is kind of showing on my screen a sort of walkthrough, and then it's sort of best for you to kind of do it on your computer and follow along, which means that for folks who are on one screen, I guess you're going to have to be kind of switching in between. And so please let me know if I'm going too fast, or if you need me to sort of explain more. yeah, I'm happy to take my time here and slow down. And this is kind of the way that we're going to be doing for doing this for most of the course, where I'll have essentially like a whiteboard teaching time, and then we'll show how to actually implement it in the code. So yeah, like try and figure out a system that best works for you, and definitely let me know if you need to slow down, if you need me to slow down. Okay, so everyone should open up their RStudio, and I'll just give a quick. I actually don't even have RStudio on my computer because I do everything. Well, I'm actually gonna switch to RStudio in the future, but just for today, unfortunately, I don't have that set up, and so I'll just bring this over so that folks can see. Okay, so your screen should look something like this. And this is a sort of basic example of the layout. This is going to be your source code, and then this is going to be your console and terminal. So again, this is just going to be for today. I think it'll be easier on Wednesday to follow along. But this source area is going to be on the left side of my screen, and then the console terminal is going to be on the right side of the screen. And the reason why I'm encouraging folks who are new to this to use RStudio is because it actually has a couple other sort of nice built-in features that you can see here: the environment history and the files, plots, packages, and help tabs here, which let you kind of move around and interact with the environments in a more sort of like point and click manner, as opposed to programmatically. Okay, so with that in mind, I will open up my console. So again, what I had called the source on the left, which should be your top left, that is known as an editor. So this is kind of analogous to a notebook. You can write and store commands here into the editor. So, blah, blah, blah. I can write this stuff here. And then you can feed this into the console line by line or in its entirety. And the console is the command line interface. So you can perform line by line operations here. So let's give an example of that. So we can start out with some basic operations. And so what you'll see here is this is kind of shaded out in gray. I have the pound sign or the hashtag sign, right? And that is denotes that everything in that line should be a comment. And so when you do that, it's kind of like you can make notes in your you can make notes in your editor about the code that you're doing. So I could do simple addition, so 1 plus 2, right? And so this can be executed into the command line in RStudio. The way that you would send that command into the command line is with let's see, let me bring this back up. So you can see right here, there is a little button that you can press that says run. So if you hit that on the line that your cursor is on, it will execute that line of code. You can also, as a shortcut, press Control Enter on a Windows computer or Command Enter on a Mac, and then that will execute that code. So hopefully, if you guys are experimenting around, you should be able to do that. And on mine, so it'll look like this when you execute the command. So 1 + 2 is equal to 3, and so there you have it. You can do multiplication. And that will give the answer there. And you can do exponentiation, so 3 to the 4th power there. And so, yeah, so it's acting basically as a simple calculator so far. And one thing to note is that, you know, I can do things specifically in the console. And if I'm just, you know, if you're like just quickly doing some operations, you can do it like that. And it's not going to get saved or stored in any way within your editor. So all the content that you want to save for yourself, you can keep it sort of in the editor and be able to run it again later. But anything that you execute in the console, once I clear the console, none of that is saved. It all sort of disappears. Okay. Yeah, and again, feel free to chime in with any questions. And if you don't feel like asking live, you can also type it in chat as well. I try and keep my eye on that.
So I have a question.
Yep.
So on my dashboard, I can see only 3 boxes instead of 4 that you showed us.
Ah, okay.
I don't know what could be wrong with my
Let's
studio.
see. Okay, so you probably see this box, this box, this box, and this box. Is that right?
Yes, so it seems the source and the console are in the same place.
Yeah, so probably what you have is a source box that looks like this. It's taking up the whole space.
Yes.
So you want to, oh man, you have to start a new console, and then I think you click this guy up here, which should like size down the source so that you can see the console. Hopefully, does that work?
No.
Create a new
Yes,
file.
yes, it does. Yes, it does.
Okay.
Thank you.
Yeah. So yeah, I didn't see who was speaking, but it's been a while. Yeah, sorry.
That's
It's been,
Yemi. I'm
oh,
Yemi.
no. Yeah. But someone else was just chiming in, and I wanted to ask, because sometimes you have to start a new console, and I don't remember how to do that in RStudio off the top of my head. If you're familiar, do you want to remind the class how to do that? I think, okay, well, I think it's in, and this is something that I can go over once I get RStudio set up, but I think it's in like file, and you have to start a new console or terminal. But okay, hopefully everyone is able to get that up and running if you click this button. I think by default the console should be there. It might just be minimized. Okay. Yeah, so there might be a maximization button at the bottom of the source page.
Yeah, I think the person who chimed in suggested to open a new file. Like I just opened up R from scratch, and it just had the console on the left side.
Oh, okay. So if you're missing the source file, you would hit File, New File, and it should create the actual editor window that you want. Okay. So let's move on. If folks aren't or if we've got that sort of sorted out. So storing data as objects. So the way that the sort of traditional way that we do this is with this arrow notation. So this means x is going to be stored as a value equal to 2. So I can do this, and then if I call x again, and I just hit enter, it's going to return the value that I stored it as. So I've essentially assigned that value to the letter x, which is now a variable. And in RStudio, so I can look at the things that I've stored with this command called ls. Okay, don't worry about this stuff. It's actually a default setting for my program specifically, but you'll see that now x is stored here. And the nice thing about RStudio is you have a default way of looking at that, which is up in here. If you've stored x, you know, as the value 2, you should be able to see in your environment that showing up here. Okay. So if you work in other programming languages, the way that you usually store an object is x equals 2, which you can actually do in R. So actually, let me do something different. We'll say x equals 3. So if I do that, and then I look at x, it's going to return as 3. And so equals works like the arrow assignment, but there is a really sort of nuanced reason as to why you shouldn't do this in R, and I won't get into it. If you want to look into this on your own, there are edge cases where it's kind of dangerous, quote unquote, to do it with an equal sign as opposed to doing it with generically with the arrow notation. And so I'm just gonna encourage you guys that when you do variable assignment, that you always use the arrow assignment as opposed to the equal. And one thing that I'm just going to put down as a note for everybody is that, and we'll talk about this a little bit more later, but equal is an assignment operator, and then there's a different operator, again, which we'll talk about later, which is equals equals, and this is a condition check operator. So for example, if I want to say, does x equal 3, then it's true. Does it equal 2? It's false, but if you do that, it's going to assign it as 2, right? So it'll be different things. Okay. One other thing to keep in mind is that R is case sensitive. And so when we're talking about variables or function names or anything of that sort, just know that capitalization does always make a difference. So if I look at capital X instead of lowercase x, it's going to say object X not found because we never assigned the capital X to any value. Okay, so I'm also going to create a variable called y, which is going to be 3. And so I can look at my stored values. X is 2, y is 3. And you can just look at them with simple operations like this. And then I can actually do specific operations. X plus y is 5, and that's because x is 2, 3 is y is 3. Okay, straightforward. And actually, I already kind of showed this, but you can overwrite the assignment. So if I say x is now equal to 3, and then I do x plus y, my answer will now be different. It's now going to be 6. And so when you are doing this kind of coding, just remember to keep in mind that as you assign variables, it is possible to overwrite them, and you get sort of weird things happening or unexpected things happening if you do that. Okay, great. So the very first thing we're going to do is to look at concatenate function. So I'll stop here and maybe quickly explain that when we think about functions, a function is something where I have a specific input, and then I'm going to have a specific output. And so there are lots of built-in functions where you have something that goes in and then something that goes out. And you can build your own functions, which we'll do in a moment, where you define what input you would like, and then given what you kind of write about the function, it'll determine what comes out. So this very first function is called the concatenate function, and it's probably one of the sort of most generically useful ones, where I can put a whole bunch of numbers together into like a single vector. And so the way I would do that, 1, 2, 3, 4, is with this C. So C is the function that stands for concatenate. And if I run this code, it will put all of the numbers together into a single vector. Okay. And so this number here designates like an index for the object. And so this object contains the numbers 1, 2, 3, 4. And you can put any sort of numbers that you want in the concatenate function. So 2, 5, 7, 8, right? And if I run this, it'll just create a single vector that contains all of these numbers. Couple shortcuts, or I'll say one shortcut for now, is that if you just want a list of numbers that go all the way from one number to another, you can do that with this abbreviation, colon, right? And this will give you the same thing. It's one vector with everything in between. And that's going to be a lot easier than if I wanted to go all the way to like 99, right? I don't have to type this all the way out and so on and so forth, right? I'll just comment that out. I could just do 1 to 99 and voila. So very easy to create. Okay. And so other things to know about vectors, so operations with vectors. So let's make a couple vectors here. C 1, 2, x2 is going to be also 1, 2, and x3 is going to be 1, 2, 3. Okay, so let's run these, and then I could just look at them really quick to make sure, right? X1 is 1, 2, X2 is 1, 2, and X3, oops, X3 is 1, 2, 3. Great. So if I do X1 minus X2, maybe try and visualize what you think is going to happen here. We'll get 0, 0, right? It's going to subtract the first element of the vector x1, which is 1, from the first element of the x2 vector, which is 1, so that equals 0, and then it subtracts the second element from the second element. Okay, let's think about what would happen if I subtracted them. And so maybe think about in your head, what do you think this would be? Okay, So something happened here. We got this warning message. So it did give us an answer. So in x3 minus x2, the longer object length is not a multiple of the shorter object length. Okay, so a couple things to keep in mind here. There's two types of, I guess, messages that could happen when you do something unexpected in R. The first is what we see here, which is a warning message. And so when you get a warning message, the code will still execute and you'll still get like a real outcome. But you can like look at the error message to see what it's saying. And then the other type of thing that could happen is an error, in which case the code will stop running and you won't get an answer because it's not able to produce something. You've got something essentially wrong in the code. So in the warning message, one of the things that you'll notice is that, okay, x3 has 3 elements and x2 has 2 elements. And so for the first 2 elements, it did kind of what we expected. It's 1 minus 1 and then 2 minus 2. But in the warning message, so it's giving us a hint of what's happening, but essentially it goes back to the beginning for x3, or sorry, for x2. So on the third element of x3, it does 3 minus the start of x2, so 3 minus 1. So what happens when you subtract 2 vectors? It'll loop back to the beginning of the vector, and that may or may not be the behavior that you want from it, but that's kind of what's happening. So it's important to keep this in mind when you're doing certain types of operations. So this isn't even necessarily about these vectors, but understanding what's happening under the hood will ensure that you don't have results that are unexpected to what you're trying to do. So hopefully everyone can see what's happening. So if I do 1 to 6, so there are 6 entries here, which is a multiple of the shorter object length. So if I do x1 to 6 minus x2, so now you're subtracting a vector with 6 elements with a vector of 2 elements. Okay, you can see that it's, that every 2 elements are getting subtracted by 1 and 2, right? So 1 minus 1 is 0, 2 minus 2 is 0, 3 minus 1 is 2, 4 minus 2 is 2, and so on. And so in this case, right, you might not get any error message at all, and that's where it starts to get really dangerous if you don't know what's going on. So some people might think that, oh, it might just subtract the first 2 elements and then ignore the rest. But you have to know, what's going on in order to see that. Okay. What happens if we go the other way around, where we have 2 elements subtracting 3 elements? So same type of behavior where it loops back to the beginning, but for the one that is being subtracted from. Okay, and so hopefully that means that you can see, or you can predict what's going to happen here. So the regular 1 and 4, 1 times 1 is 1, 2 times 2 is 4, that's fine. x2 times x3. Okay, I predict that we're going to have, right, the same warning message and that it's going to loop around. So it'll be 1 times 1, 2 times 2, and then 3 times 1. So I think the output should be 1, 4, 3. So let's see if that's the case. Yeah. And then you can also do division of vectors. 1 and 1 makes sense. And I can multiply a vector by a scalar. So if I do this, it's just going to multiply every entry by 4. So 1 times 4, 2 times 4, and 3 times 4. Okay. Let's do some matrix multiplication. So this is going to be a little bit more uncommon. I'll occasionally do this kind of stuff, but it's fairly rare. But anyone who is working with matrices and that sort of thing, you can actually do matrix operations. So if I want to do matrix multiplication here, if I do x1 times x2, you can return a matrix C with the answer, right? So it's 1 times 1 plus 2 times 2, which equals 5. You can also do the transpose of a vector here. So usually they denote vectors as like a column, and so doing the transpose flips it into a row. And we'll talk a little bit more about data structures and data types later on. And so if don't worry about getting too confused here. Okay, so this is actually a good time to take a quick break. So I should mention that by popular demand since last year, since it's all sort of online, I do 5-minute breaks sort of halfway or about halfway through each of my lectures, give everyone a quick chance to use the bathroom or anything. So we'll do that right now, and I also will kind of just stick around here, and if anyone wants to chat or have any questions about the lecture or anything else, I am available during these 5 minutes. So we'll stop until, let's say, 3:02.
Professor, just to ask, this T, what's the function for this T? Is it transpose or something?
Yeah, this is, let me, I'll put it in the notes here. So transpose.
Thank you.
Yeah. And it's a little bit more useful for like matrices. So I can show like a quick example. I know we're not going to cover matrices today, but let's see if I do something like this. Yeah, okay. So this matrix has 2 rows and 3 columns, and it goes, 1, 2, 3, 4, 5, 6. And if you do the transpose of that, it'll flip the matrix like so.
Thank you, that's clear.
Excuse me, Alan, are you there?
Yep, I'm here.
Oh, okay, thanks. I was just wondering, like this line 42, you know how it
Yep.
says multiplied by percent and then x2. So I've seen this in like the dplyr, they kind of have this percent greater than percent. And I've always kind of found it confusing. Like, how do you read this?
Okay. Yeah, so that's really different. That is, okay, so, and actually, I'm one of the few people who don't use dplyr as much. But okay, I just want to be really clear that this operation is a specifically matrix multiplication. And in dplyr, this is called a pipe. And it tells you to continue an operation in the next line to the sort of previous set of tasks. So yeah, this specific notation is quite different from what I'm showing over here.
Mhm.
So dplyr, let me see if I can grab a quick example. So actually I need to load the library. So if you yeah, these examples are usually better if there's some kind of like grouping or something. But essentially, if I wanted to perform some kind of like function on my original thing, whereas you might have some kind of breakdown of your x1 within the function like this, the way dplyr works is you can do this pipe, which lets you do operations in sequence. And the reason why they do this is if you do it kind of line by line, many people consider it to be easier to interpret than having sort of one longer line.
Right.
And what I'll actually do is once we start getting to things where you do like grouping functions, I will try and provide a couple examples of that. So that it'll be easier to, or so that you'll understand what's going on in the sort of dplyr world.
Thank you. Yeah, I was wondering if they're related in any way. So they're not. It's just
No, these are yeah, completely unrelated. Yeah.
Thank you.
Okay. So it's been a couple minutes now, so let's hop back in and let's look at some examples. Examples of built-in function. So as the class goes on, we will be exploring sort of more and more specific statistical tools that are going to leverage functions that that people build and add into R as external libraries, which you can load. And today we're not going to look at any of those. We're just going to look at sort of the built-in functions, many of which are going to be kind of like the bread and butter for doing a lot of the data analysis that you do. And so the very first one that we'll look at is called the help function. And this does essentially exactly what you think, or hopefully, if you put in help, right? So remember, a function is all about inputs and outputs. And so what do you put in the parentheses, which is where the inputs goes, and then what do you get out of it? So the help function, you put in a function name. So what's the first function we learned about? The concatenate function. So if I just go ahead and put C here, it should, wait, okay, I'm not sure. I don't remember if I need to put quotes. No, I don't. Okay, so in your console, it's going to open up in this area the help tab with the documentation, with the like default R documentation. And so if you do help C, what you guys should see is essentially this. And this is R's default documentation. You should get used to kind of seeing this and understanding what's here. And in fact, maybe I'll show a couple examples of different functions here. But this, there's a description, a usage, the arguments, which is what I'm calling are the inputs, right? The argument inputs. So objects to be concatenated, whether or not it's recursive, use names, and then there's some details about the function. And really useful is down here at the bottom, there are examples of ways you can use the concatenate. Okay. So the other one that I showed was LS, which I'm pretty sure that stands for list. So this is the thing that shows you what's in your working environments. So ignoring the first three, it's the X, which we define X1, X2, X3, and Y, all of which you can see up here, right, as objects that we've defined, X1, X2, X3, Y, X. So that's kind of what we're working with right now. So let's just really quickly take a look at the help file for this. And we can see that here. So ls lists objects, and it's again description, usage, arguments, and then some examples. So okay, so let me describe a little bit. Well, okay, I'm not going to do it for this one because this one I actually don't even know. This is a little confusing. These details we probably would never use. I'll go into the arguments in a different one where it's more amenable for us. Okay, RM. So this is the remove function. And so what you do here is you put in the object that you want to remove from your workplace. So let's say I wanted to remove X1. Okay, so now if I do ls, X1 is no longer there. And if I call X1, it'll say object not found, right? And we had defined X1 earlier as 1, 2, but by using RM, you've removed it from the workspace. So if I wanted to put it back, I'd have to redefine it like so. We have a function called mean. And mean will take an object, and it will take and it will return the average value of the numbers in that object. So X1. So the average of X1, which is a vector 1 and 2, is 1.5, right? It's 1 plus 2 divided by 3. Great. Let's see here. So let's actually take a look at the help file for mean. And let me see. Okay. This is an R object. So this is the object that you're putting in. But there are actually, oftentimes you'll see in the function description and usage that there are other things that you can put in here. And this is described, the arguments are described here. So let's show you how to use this. So na.rm is a logical value indicating whether NA values should be stripped before the computation proceeds. So let's say you like load in a data set and one of the columns has a set of values that you want to work with and you want to take the average of those values. So unfortunately, as you guys will find in sort of your real life research, that data sets are usually quite dirty. And so you may end up with let's say Z. Let's say you have a bunch of numbers within your data set, but you also have an NA value, which is like a blank value, something that's omitted, or that the data just doesn't contain it. So if I look at this vector, that's going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, and then it's going to have my blank value. Now, if I take the mean of Z, it's just going to give NA, right? Because how does it know how to deal with an NA value? It doesn't. And so if there are any non-numeric values, then that function is essentially going to like break. So if you saw from the help file, one of the things that we can do is this option, which is a logical value indicating whether NA value should be stripped before the computation proceeds. So they've built in this thing where I can do na.rm is true. And if I do that, then it's going to remove the NAs and then compute the mean first. And this way, I'll actually get the real average value. And so when you look at these help files, that is, one of the things, like the actual options and like tuning things that you can do within the function. And all those arguments will be listed under this section. All right. Anything confusing here? Not straightforward? Let me know. Otherwise, we will move on. Actually, sorry. Before we move on, I'm gonna also, so we did this. We did mean of x1. Right, and we know that x1 is a vector 1, 2. So I want you guys all to quickly visualize in your head what you think is going to happen if I do mean 1, 2. Okay, so I'm going to hit enter, and it's going to be 1. Okay, so if you're confused about this and you thought it was going to return 1.5, we have to think back as to what is going on here. If you look at the help file, the argument that needs to get passed here is x, which is a single object. Okay. So when the easiest way to think about this is that when you put arguments into a function, each object is separated by a comma. So really what I asked it to do was to take the average of 1. You can't just put in a string of numbers and think that it's going to evaluate all of those, because functions may have multiple arguments and you are like putting in objects into each of those arguments and not putting it in as a single object. So really the right way to do this would be like that, so that the numbers 1 and 2 are concatenated into a single vector object for it to be able to take the mean. Okay, and so do be careful about the difference between this and this. So we'll say correct is mean 1, 2. Incorrect is mean 1, 2. The next function that we'll think about is called length. This is also a really handy function. So let's see here. Let's go ahead and look at length of x1. That's 2. Length of x2 is 2. Length of x3 is 3. And then I made another one here, didn't I? Let's say length of z, that's 10. So the length is an operation that you conduct on a single vector, and it tells you how many elements there are in that vector. Yeah, and so that's a really sort of nice, easy, simple way of being able to say how long, you know, a specific vector is. And analogously, so we haven't really talked about matrices or tables or data frames or anything like that. But when we get there, there are similar types of operations. There's a function called nRow and a function called nColumn, which will tell you how many rows and columns there are. So I'll just put a quick example. So don't worry about like the structure of this or anything, and any of the syntax. We will cover this later on. I'm just showing you an example table, which we call data frames in R. So this table looks like this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And you can look at the number of rows of this table and the number of columns of this table. Okay, and so you might think this is really silly because I could just visually look at it, but sometimes you may be working with tables that are so big that you have no ability to look at that feasibly on like your console. Like it may be a table that might be even too big to look at in Excel, right? And in some cases, even opening it could to view like manually, like on a spreadsheet, could crash your computer. But with nRow and nCol, you could really easily be able to get the size and dimensions of the table. So this is actually a really handy function and something I use like all the time. So yeah. Okay. Let's do example. Okay, so I'm just going to make another object called example vector, numbered 1 to 100. So it contains all the elements 1 through 100. There is a function called max, which hopefully you guys can guess what this does. It returns the element, the largest element of the entire vector. Obviously, there's going to be one called min, which will do the same thing, but it'll give the smallest elements of that vector. Okay. There is a function called sample. So sample function, x size. So I always mix these up, but you can actually see mine does it, and RStudio has this as well. You can see right here below my cursor, it tells you what the inputs are for the function. So x and then size. So let's do an example of this. So the x that I want to sample from is the example vector 1 to 100. And let's do 10. Let's have size equals 10. So one other thing to mention is that when you do the arguments, it goes in this order, but you can actually explicitly say which one you want to like assign as that. So what that means is like I could do x equals sample vector size equals 10, or I could do sample. This is the abbreviated version, but it's usually good practice to write it out so that you know what's happening. So this is abbreviated. This is, oops. This is full. Okay, and so the sample function is like drawing out of a hat. Okay, so I have this hat and I put in the numbers 1 through 100, and then I'm going to reach in and I'm going to pull out 10 of those numbers. And then that's going to happen completely randomly. So the 10 random numbers that I happen to pick out of this hat are sort of set here. If I run this again, it'll be a different set of numbers. You can actually make it so that it's not random with something called set seed, but I won't talk about that right now. But what I do want to do is see what happens when I do size equals 99. Okay, so it's going to sample 99 of the numbers out of the hat. What if I do 100? Okay, and so if you took some time and you look through this, what you'll notice is that no number is repeated twice. And in fact, actually I could do that with something called order. So it's this simply order. No, did that not work? Oh. Okay. You have to do something like this. Example. So don't worry about learning this part yet. We'll get into how this works later on. This is just to show you if I were to take all those numbers and then order them from the sample, you'll see that it's just all of the numbers repeated. So now think to yourselves, what do you think is going to happen if I do this? So I put 100 numbers in the hat, and I want to draw 101 numbers out of it. Okay, it's going to give you an error. So this is the counterpart to the warnings that I was telling you about. This time it gives an error, which means that it actually can't run it. And it tells you, okay, it cannot take a sample larger than the population, which makes sense, right? If I want to reach in and grab 101 numbers, but there's only 100 elements in there, I can't get 101 things. But you can do something called sampling with replacement, which means if I reach in and pull out a number into the hat and pull out a number, I will then put that number back in and then reach in and pull it out, sample again from the hat. And so this time, let's do, so okay. Example vector, size equals 101, place equals true. The default is replace equals false. Okay, and this time it does work because I put the number back into the hat before I draw out another one, which also means that I should be able to see some repeats. In fact, we know that there has to be at least one repeat because you've drawn it 101 times. Okay, so if I assign that and I do the same thing where I order it, again, not worrying about how the syntax works, just looking at this. Okay, we can really easily see like 2 got repeated 3 times, 10 was repeated 3 times, 11 was repeated 1, and so on. And so you get a bunch of repeating values, which is what happens when you sort of draw numbers out of that. Okay. Let's continue onwards unless there are any specific questions about this. Let's look at a function called rep, which is short for repeat. So rep short for repeat. Okay, so let's do x3 2 times. So it's going to take my vector x3, which is 1, 2, 3, and it's going to repeat it twice. And you could actually even do this for a single number. So just really quickly to demonstrate, if I wanted to repeat the number 1 100 times, this will create a vector with the number 1 100 times. Let's look at the help function really quick for rep. So x times length out. So instead of saying number of times to repeat, so this is like times equals, you could actually give it a final length dot out, and that would tell you how many, how long it needs to be. So like if I wanted to do x3 length dot out equals 100, I actually very rarely use this part of the function. So we can see how this works. Oops. It's just going to give 1, 2, 3 repeating until you have 100 elements in that vector. So this is a pretty handy function to do data manipulation. Let me do this just so we can see. So 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. You can also have an option called each. Let's see what this does. So instead of repeating each vector, it repeats each element of the vector that many times. So each 4 times, so 1 gets repeated 4 times, 2 gets repeated 4 times, and 3 gets repeated 4 times. So these are different ways that you can use rep, and you could actually mix and match and do both of them. So x3 times equals, let's say 3, and each equals 4. So 1, 1, 1, 2, 2, 2, 2, 3, 3, 3, 3, right? So that's the each part, and then we're going to do that part 3 times. So you get 3 of what I'm highlighting here. So 1, 1, 1, 1, 2, 2, 2, 2, 3, 3, 3, 3, and so on. Okay. Let's see. Sequence or SEQ, short for sequence. So I give some example of how to do a shortcut for concatenate. So like if I want to do like this, that takes a little while to write. And so instead I'll do that. So the generic way of being able to do the shortcut is to do a function called sequence. And that has these options from and to. So if I wanted to do from 1 to 10, I could do that. So there's my manual one where I type them all out. Here's the big shortcut where I do the colon and then sequence from 1 to 10. They all give the same thing. So the power in the sequence argument is that I can also sequence it by specific intervals. So, okay, so if I want to do it every 2 from 1 to 10, so it'll go 1, 3, 5, 7, 9. And that's not something that you'd be able to do with this colon shortcut. And you could do it with this, but say you wanted a much larger vector, you wouldn't want to, type that out. And in fact, you can do this in smaller increments too. So if I went by 0.1, then it's going to go 1, 1.1, 1.2, all the way sequence out to 100. So sequence is generically a more sort of powerful function to do sort of patterned values out into a vector. Okay. Another function that I use very, very often is called unique. Probably one of the most helpful functions that I encounter. If you want to return all the unique values of a vector. So let's do example.unique. Let's actually repeat one of these. Oops. What am I doing here? I want to create, sorry. I want to create an object called example.unique, which is when I repeat each of the values in x3 4 times. Okay, so we can see what this looks like. 1, 1, 1, 1, 2, 2, 2, 2, 3, 3, 3, 3. And if I do the unique version of this, it will return just the unique values of that vector. Okay, this is really handy, for example, if you're like working on a survey and you get tons of responses, and you just want to see what are, for example, what are the unique responses for this particular question. You can do that, and it just filters everything down, right, to the answers that you want. So this is definitely one of the functions that's quintessential for like exploring new data sets, and you want to understand the data. You'll be employing this function to look at what's contained within specific columns or rows. Okay, and then we've got summary and SDR, which I always forget what that stands for. Structure, I think. Yeah, structure. So I will actually hold off on these particular functions until we start messing around with tables and that sort of thing. These help describe essentially what's in the table and the components of the table. But we'll get into that in next class. Okay. So now that we've kind of explored a couple sort of select functions that I've chosen, which I think are generally going to be fairly useful, you know, take some time to mess around with these and make sure that you sort of familiarize yourself so that you understand exactly what's going on. You know, oftentimes there's going to be a little bit of disconnect between sort of me explaining it and then you sort of really understanding what's going on. So I encourage, especially those who are new to this, to go back in and kind of play around with these functions and make sure you really kind of see what's going on. You know, put in different values, see what works, what doesn't. And I think that's kind of the best way to learn this. So now that we've covered a lot of these basic functions, we're gonna explore creating your own function. So let's see, building custom function. So the way that you create your own function is kind of in the following way, but it follows along a lot of the basics that we've talked about, right? So I'm going to create a function called I'm real mean. Okay, and so this object is called I'm the real mean, and then we're assigning it, right? And then the thing that we're assigning, instead of a value, we're going to say function. And then this function is going to have some kind of input. Okay, and we're trying to build it to be similar to we're trying to build it to be similar to the function called mean. So how do we take an average? We take all the values within an object and then we add them all up. Okay, and so if our object is called input, x, I'm going to call x input, y is length input. And so, okay, we didn't actually talk about sum, but hopefully you guys can understand what this is going to do, right? Sum is going to add up all of the values of my vector. We did talk about length, which tells you how many elements there are in that vector. And those are the two components that we need to determine what the average of the value is, right? Use the sum divided by the length of that object. So z is going to be x divided by y, and we're going to do return z. So return tells the function to have that thing as the output, right? Because we're actually calculating a couple things. We have an x, a y, and a z, and the thing that we care about is the z, so that's what we're going to put in here. So I'm going to go ahead and run this function. So now this function itself, I'm the real mean, exists as this function that you can employ similar to the way that we're using a lot of the built-in functions. So let's say I'm the real mean, and I'm going to look at x1. Okay, and so x1 is equal to a vector of 1 and 2. So when we did mean, it gave 1.5. And so if I run this function, I'm the real mean, x1, it's going to give 1.5. Okay, cool. So that did what we expected, right? And so that is kind of like the basics of how you write your own function to do the things that you want. And as you can imagine, this is a very powerful tool you can create much more complex functions that enable you to do all sorts of sort of interesting things that you would want in data analysis or whatever it is that you're doing. Okay, so one of the things, okay, so now we need to get into some of the details about the function that we've only kind of scratched the surface on here. Okay, so I'm gonna scroll back up and I'm gonna look at all this code that I've written. And actually, you know what, well, let's just do an ls. And so you can see in this ls, or on your RStudio console, right, you can see over here all of the variables that we've already defined. And so we've defined x and y, and in fact we've also defined the z. And remember what I was saying, that when you define a variable, you can overwrite it later on if you redefine x. So let's look inside of our custom function. We actually have x, y, and z, and we've defined them as something different, right? So our original x and our original y actually, they're coincidentally going to be the same. Okay, let's do this. X equals 10, y equals 20. I'm going to run this again. I'm going to run I'm the real mean again. Okay, so I redefined my x and y, and then I run this function, or I define the function and then I run it. And when I run it, it takes in my x1 input, and then it defines x as something, it defines y as something, it defines z as something, and then it returns the z. Okay, so let's put in x here and visualize what you think is going to get returned when I hit enter here. Okay, it returned 10, and y returned 20, and z returned 1, 2, 3, 4, 5, 6, 7, 8, 9 with the NA, which was that earlier example that we did. Actually, I didn't even write it in the editor, right? But up here we define Z as something. Okay. So maybe you're expecting that this X should have been the sum of my input, which is, sum of X1, which is 3. Okay, and so why didn't that get replaced? So this when you create a function, everything within that function is its own domain. Okay, so we have in your RStudio, you have this thing called the environment, and you actually have what's known as a global environment. And so everything that we're defining, like out here, outside of a function, gets defined into your global environment. But anything that happens within the function does not affect objects in your global environment. And there are a lot of programmatic reasons for why you do it this way. One of the most, I think, fundamental ones is the fact that you're not. It allows you to keep a broader namespace, which is like the space that I have to name my variables. And so by doing that, I can call these guys anything that I want, and it has no effect on your quote unquote sort of outside world. And so when I go back to call my X and my Y and my Z, it is not having to do with the X, Y, Z within the function. So that's one sort of key thing to keep in mind. it is for a lot of sort of programmatic reasons, this is the kind of standard for almost any programming language, is that you won't have conflicting namespaces outside of functions. And you can imagine why this is really useful, right? Like if I, for example, have two different functions that use the same namespace, you could cause all sorts of like really wacky behavior. And you wouldn't want that to happen because, you know, if I use one library or package from one user and another library and one package from another user, you don't want those variables, you know, like using a variable X, for example, which is really common. You don't want that to be messing with other functions, okay? So I will show how there is a way in which you can have the environment within a function affect the global environment. And that is with this double arrow here. If you have these two carets, that means write out the, or do the define X, but into the global environment. So if I run this right now, and then I go ahead and do I'm the real mean. So, and if I look at X, it will no longer be 10. It's actually going to be 3. So I don't know why I always show this. Don't do this. It's a really bad practice, and it gets people into trouble. Yeah, there has to be some really exceptional thing for you to want to do this. But it is possible, and this is how you do it. But I'm not even going to include it in the notes because it's bad practice. So don't do this double arrow notation. Yeah, it'll just get you into trouble. Okay. So let's see, should we? Yeah, actually, I think I will end here. This is kind of a good spot to stop. We'll get to the logic and truth table stuff next class. So yeah, before everyone takes off, I guess a couple other things to keep in mind, or announcements. So like look through the syllabus to make sure you know where we're going to be at with everything, and that's also kind of as a reminder, one of the things to put on the calendar. I made an announcement for those who didn't see it. So next Wednesday, actually, I am getting my second shot, and as kind of a precaution, since I may or may not have side effects, I'm actually going to pre-record that class the night before on Tuesday evening, and I will upload it to Canvas and YouTube. So you are welcome to just, you know, watch that whenever you want. But I'm also going to be doing it in the same sort of format on Zoom. So if anyone wants, you can show up to that class in the evening, you know, if you have nothing better to do. But there's no expectation to show up to that. I'm just gonna, you know, record the lecture as usual. Let's see. Anything else on the Canvas? I was going to say something, but I don't. Oh yeah. So okay. So the other thing that I want to say is that I have these PDF notes of the lectures, which I'll be posting to Canvas after every class. And so, you know, this actual document that I was showing is coming from the notes for today. And so, yeah, and this won't just be for the tutorial. This will be for the whole class. And so make sure, you know, to check that. You know, I think that students have typically found these notes to be pretty helpful. They're fairly comprehensive on the material that's covered, and it gives kind of the contents as well as the examples in class. So if you've missed anything, you'll be able to find it in the notes. Yeah, okay, and I guess that about wraps it up for today. I will see everyone on, see all of you guys on Wednesday afternoon, and yeah, in the meantime, I'll stick around a couple minutes after if anyone has any questions or concerns or wants to talk about anything. See you all